Yes, we are live now.
Bhavna, I think we can start now.
Okay. A very good morning to everyone. We would like to welcome Dr. Ajay Kumar Chauhan, sir, Honorable Resource Person for the day, my colleagues, and all the participants to another day of this faculty development program. In continuation to yesterday's lecture, today's session will be conducted by Dr. Ajay Kumar Chauhan, sir, on time series analysis. We look forward to hearing from you, sir. Ajay, sir.
Yeah. So good morning to all of you. And today is the day for time series analysis. So welcome to all. And because it is an introductory session, so I will just start the time series analysis. And let me show you the slide. Okay, please allow me to share the screen.
Host. Okay.
Ravinder, you are host now.
Okay, just a second. Yes, sir. You can. I
Yeah,
think.
I'm now sharing my screen. So this is the coding of R which I am going to discuss today. And these are the packages which you can see to download. And I already downloaded these packages. So I will not install it. And I will start from the library function. So there are different packages we use in time series analysis. And if I want to run it, I just click on run. And all the packages are there for use. Now I can use all these packages. After that, you know that whenever we start working on our package, we must define some folder where we put all the files. So this is the path of my folder where I put all the data set, and whenever I require, I can call them, I can import these data set. So this is the path of my folder. So let's run it. And get WD will confirm whether the computer understands the same folder as I provided to the R package or not. So I have checked, I have to match the path which I gave and the path which computer understand. So both are same, so no problem. Now I'm going to open a file. This is a time series data set, and we are going to apply some of the basic functions on this time series data set. So let me show you the data set first. In this case, IIP means I am using the IIP as a name for the data set, and read.csv, you know that we are importing the data set by read command, and iip.csv is the file which I just want to import, and header equal to true means whatever is written in the first row is considered as the name of the variable. So let's see the file. Okay, now file is imported. You know that the software is showing no problem here in console. So I enlarge the console and the script file so that you can see each and everything clearly. And now I want to see the first 6 observations of the file. So I am putting the head command. Head command will show the first 6 observations, and the first 6 observations are these. So you can see that the first variable in this file is the date, and I have the data from the 1st January 2006, and up to what I have to check by giving the command tail command. Uh, this is the value of IIP. IIP stands for Index of Industrial Production in the country. It is the actual IIP data of the India. And the third variable is time. This is just for applying the regression model. It is a time variable 1, 2, 3, 4. And because we are having the monthly data, so these are representing the month. And D January up to D December are the month dummies. So month dummy means when the month is January, I put 1 to D January. Similarly, in dummy of February, whenever the month is February, I put 1, otherwise 0. Similarly, I created the 12 dummies of all the months. This is for the purpose of capturing the seasonality in the behavior of IIP. Okay, now after that, I am running command tail of IIP. And tail means if I want to see the last 6 observations, then I can run command tail. And the tail is representing that I have the data up to 12 December 2017, and there are 144 observations in the file. And 144 observations is of basically, if you divide it by 12, it is approximately 12 months, 12 years. We are having a 12 years data set, monthly data set, and yeah. And if the name command, if I run the name command, I can see all the name of the variables in the file. So the first variable is date, IIP, time, dummy of January to dummy of December. Now I'm giving a one command, attach command, because you know that the problem is that if I don't give attach command, I cannot work on the variables. For example, I'm showing you, if I run the command mean IIP, the software will say no, I will not run this command. Why? Because we only have the data set, we are not having the uh, variables. So if I apply the mean of IIP, you can see that the error comes that object IIP don't found, because actually up to this level, this IIP is a black box, and it is a data set, it is a box. Whatever is there in the in between under this is not clear. So first of all, we have to attach the file. So I am now giving the command attach file. Now this box is divided into the matrix. Matrix includes the observations, which means row and columns. And now if I run the command mean of IIP, the software will give me the mean. This is just to demonstrate that what is the importance of attach command. Uh, so after that, after giving the attach command, and now I'm going to find out the structure of the variables, because a structure of the variables is important, because in time series all the variables should be integer variables. You can see that all the variables are integers, means numbers. So I'm happy, and I can run further analysis on it. In case if any of the variable is a factor variable, then it is a problem for me, and I have to check why it is a factor. Factor means alphabet. So whenever we deal with the time series, we should confirm that all the variables should be integer, not a factor. There are two possibilities in it. The variable could be integer, variable could be the numeric. If you have decimals in the numbers, then the software may show then numeric. Otherwise, it is showing integer. So now I'm having integer that is equivalent to numeric, and we can apply all the statistics on this data set. Now let me show the plot to you. If I draw the plot comes here. Now you can see the plot. Now I'm asking you, are you happy with this plot? Are you happy with this plot? You say, sir, okay, not very good. It's just okay. It's not very good. Why it is not very good? I'm telling you. You just see the x-axis. Here the x-axis is showing you the number of observations. It is not showing you the dates. This is the biggest problem in dealing with the time series, because whenever you import the time series data set, it is showing you the observations, not the time. So the first duty of the researcher is to convert into a time series data set. So now I'm telling you how to convert a data set into a time series data set. Again, show the axis of it. And here you can see that we are not having the dates on the x-axis. So this variable, this plot cannot be called a time series plot. That is a problem with most of the time series data set. And I want to see the frequency of time series, and the frequency is found to be 1, and you know that there is no meaning of this 1. and head IIP, tail IIP, I already showed you. Basically, this is just for finding out the dates that we are having dates up to when, up to which, and up to which. So here the command indicate that we are having the dates from 1st January 2006. Okay. So we are having clarity on the type of the data set in the time series. Now, the first important command which I am doing here, converting the normal data set into time series data set. So I should write here, convert a normal data set into time series data set. So this is the first command of time series data set. Otherwise, the software will understand that this data is a normal data set, not a time series data set. So here we are defining that data set is time series. Now, R date. It is a date defined by the system of our software, and as date is the function. And for converting, I'm using the first variable, that is date. You can see this is a variable. I have a variable called date, and I am using this variable to convert it into a system date. So IAP date is the name of the variable, and I'm taking this format. So because software will read what is the format of the date. So you can see that 1 means it is a January. 1 means the 1st of the January, and the 2006. So my format is percentage month, percentage day, percentage year. So the date format that I have in the original file is month, day, and the year. So I am instructing the software that kindly read this date as this. So let's run it. Okay. So you can see that the software uh, successfully execute the command, and now I'm converting this date into the system date by clicking on the fixed date. Okay, so this is a our date system in our software. It is very difficult to understand that. So, but if you have this kind of answer, it means R has converted your dates into the system dates. And after that, now if I run the plot command, and let's see what kind of command, what kind of graph is coming. So now you understand that this graph is better than previous graph, and but we want to add something in this graph. Let's see. Suppose I am also giving this box, so you can see that in the graph box is coming, and now I am also giving this command. So you can see that we are having the dates on the x-axis, and if I click on the frequency, now it is showing you it is a monthly data set. You may not believe that how much this command is important for you, and uh, to understand this command, I took almost a month to understand this command when I started learning R. So as a according to my experience, I shall suggest you, if you are working with a monthly data, if you are working with a daily data, so the first responsibility is to convert the date, to convert the normal data set into time series data set. And the command which we can convert is this. So first of all, you have to understand what is this command, and use this command to convert into the R system date. And after that, your data will be considered as a time series data set. So kindly remember this date. It is a very important command. After that, now because I converted the data set into the time series data set, so I'm telling you that this, if you kindly observe this, if you observe this data and the graph of the IIP, I found that this series is having a long-term trend. This series may be having the seasonality. This series is maybe having the cyclical effects and irregular effects. So a time series is consisting of different type of components, and now I want to study these different components so that I can use these different components for my analysis. So this is the purpose of the next few commands which I am going to show you. Let's see. Now I am defining the series as a Y series. So here you can see that Y is a variable now. It is a time series variable, and IIP underscore not dollar $IIP. It means I am working on the variable which is in the data set name IIP, which is starting from this date to this date. Frequency is 12. And now str, I'm just finding out the nature of the variable of Y. So you can see that it is a time series data set. You just see this command again. The software is considering this variable as a time series variable, and if you take its class, so class means which category it is. It is called time series TS. It is mentioned that it is a time series data set, and if I just run Y, this is the data set, and you can see that I'm having the month here, and I'm having the years in the first column. So first row is my month, first column is my year. So this data set is well defined as a time series data set. Okay, so in case your data set is daily data set or your annual data set, if it is a time series, so you have to tell the software that it is a time series data set. In most of the cases, we are using the monthly data set in economics especially, and in otherwise we are using the daily data set. So in daily data set, there are two systems, that 5 days a week or 7 days a week. So accordingly, you can design that what kind of dates I have in my data set. So whenever you are dealing with the time series data set, this is one of the option. You may convert your data set into a time series data set, or you can go as it is. Okay, now I just want to show you one very important command, that how to decompose this time series. Okay, let me show you that. Frequency Y is 12 now, and I'm using a function called decompose function, and the type of decomposition is multiplicative decomposition. And so let me run it. Okay, the software run this command successfully, and now you just see this plot command, because I'm going to draw the plot, and you may be happy after looking this plot. Now I'm showing you in Zoom. Yeah, so if you see this time series data set, you can find out the 4 components of the data set. The first okay, the first graph is the original graph of the time series data set. It is the original graph of the IIP. The second graph is showing you the long-term trend, and you can see here it is a trend, long-term trend. You can also see here it is a long-term trend, it is an observed series, and it is a seasonal component. So we are having the seasonal component in this series, and seasonal component is very attractive and beautiful also, you can see. And it is a random component. Random component means what is the random component in the series. Random component comes because of the unexpected shocks or unexpected news which comes into the market, and because of this the series may change randomly. So this is one of the feature of the time series, that it consists of different components, and the one of the component which we cannot see here is the cyclical component, but the you can calculate that component also very easily. Why? How? If you subtract the trend or the seasonal or the random by original series, you will get all the components. Uh, okay. Sometimes the different components are very important for us for analyzing the time series data set. And here you can see that we have identified all the components in the graph. Okay. Now let me show you one more graph. Yeah, this is another graph, another command uh, where you can see different components. This is the data, seasonal component, trend component, and the Remainder means rest of the component. Most of the remainder component is irregular, and so many times we want to analyze the regression model and or the vector order regression model. So there are different types of econometric models in the time series. Like sometimes we go for Kalman filter, Markov regime, and sometimes we will go for wavelet decomposition. So or the co-integration, Gauss model, volatility models. So in all these models, you can use the irregular component, because trend component and the seasonal components are the constant or the regular components. So we can remove these components from the series, and whatever is left may be used for further analysis. So we have different options of using the different components of the time series, and as you can see in the graph, we are having the different components. Now I am and showing you how to analyze each and every component individually. So how to analyze trend component, how to analyze seasonal component, and all. So let's come back to the console. I press Control L to clear the screen, and so I am showing you the how to analyze the trend analysis, how to do the seasonal analysis separately. Uh, Here I am applying the regression model. You can see that yesterday we discussed about the regression model. So LM is my linear model, and IAP is my dependent variable, and I'm putting the regression line. So I just write the regression line here. Whenever you want to apply the uh, trend analysis, you have to apply this equation b alpha plus beta into time plus e. So here the beta is known as trend component, and the probability value of the beta will tell you whether the trend component is significant or not. We have to check the p value of the trend component, and another thing is that we have to check the sign of the trend component, because if the sign is positive, then we can say there is a positive trend, and if this sign is negative, then we can say the trend is negative. So in this way we analyze the trend. I'm showing you the results of the trend analysis. So here I'm going to apply the linear regression. Just T I put for the representing the trend, and LM is stand for linear model, IP dependent variable. Okay, so let's run it. And now how to analyze this? Just see, this is my trend component, and this component is positive. This is by sure, because the sign of this trend component is positive, and p value, if you can see, this, and t statistic is 28.67. So we are having a probability value less than 0.05. So the conclusion is that there exists significant positive trend in the movement of IIP. There exists significant positive trend in the movement of IIP. And how much is the R square? R square is 85%. So we can see that the movement in the series is defined by 85% on the basis of trend analysis. So the trend is significant, positive, and quite high. 85% of the behavior of the series can be explained by the trend analysis. Okay. Now I just showing you the possibility of curvilinear trend, right? So we can do one thing. Let me copy this command and paste it again. Copy and paste it. So I put TC. TC means curvilinear trend, and I'm using here one more variable, time square. This is a time square. So when you include the square of the variable in the time series, it is known as curvilinear trend. And let me see whether the software is giving me the command or not. No, the software is not giving me the time square. So it means I have to apply the t square. I am converting this variable first, time power 2, and let me run this command. or now I can use TSR here, TSR. Uh, so now I hope the software will give me the trend. Yeah, it is giving me. And yeah, curvilinear trend is significant. You can see that the curvilinear trend is found to be significant. The p-value is found to be significant, but it is negative. Negative. So it means curvilinear trend is significant, but it is a negative. This is the p-value of curvilinear trend. T is negative. So what is the difference between linear trend and curvilinear trend? I'm showing you. It is a linear trend, and this trend is slightly moving here. This trend is curvilinear trend. So this is a linear trend, and this is a curvilinear trend. Curvilinear trend means the trend is slightly moving down with time, right? This is not a linear trend. This series is basically the curvilinear trend. And sometimes if the coefficient of curvilinear trend is positive, it means it is moving like this. So whenever we analyze the trend, we should analyze whether it is a linear trend, whether it is a curvilinear trend, or whether it is a downward sloping curvilinear trend, or whether it is a upward sloping curvilinear trend. So by this analyze exercise, I hope you understand what is the meaning of all these trends. Okay, now just I want to remove this trend from the original series. So you can see that I am saving the residuals of the trend series, and these are the residuals, and I am saving these residuals in the time series data set. You can see that IIP $DT. IIP $DT means IIP is the name of the box, means data set. In the data set, I am inserting one variable. The name of the variable is DT. DT I use for the D trended series. And in this series, I am putting the only the residuals. So now this is the residual series, and now I am showing you how this series look like. Okay, if you apply your common sense, basically what I am doing, I am just explaining you. This is a IIP series, and IIP minus trend, because trend is captured by the regression model, and whatever is left is called D trend. So now I have a D trended series. D-trended series. So D-trended series is like this plot. So I'm showing you the plot of a D-trended series, and just see the magic, and let me show you the D-trended series plot. Okay, so this series I'm showing you in detail. This series is a D-trended series. Means if I remove the trend from the IIP, the series looks like this. And in this series, there are two components. One is seasonal component, and rest is irregular component. So because trend is already removed from this series. Okay. Now you may want to know what is the trend, where is the trend, how can we see the trend. Okay, I'm showing you the trend. So in this command which I highlighted, I am saving the predicted values of the regression model, and those predicted values of the regression model is representing the trend. I am showing you that. Let's run it. So let's zoom it. This is the trend. This is the long-term linear trend. Actually, I remove the linear trend. If I want, I can remove the curvilinear trend also. It's totally in my if I wish, I can remove the linear trend. If I remove the curvilinear trend, so in this exercise, I am removing the only curvilinear trend, not the linear trend. And if you want to see what is the curvilinear trend, I can show you here. Let me save the plot. I'm plotting. You can see that I'm plotting the fitted values of the regression model REG and TC. So if I run this command, I can see the curvilinear trend. Yeah, you can see that this is the curvilinear trend we have in the data set. And so I hope what is the curvilinear trend and what is the linear trend, and how to remove the trend from the series. And okay, so this is just to plot the linear trend. So after plotting the linear trend, we are having this kind of data set. Okay, now let me show you the next command. See carefully. So I'm having the command that this is called IAP trend, and how I'm calculating the IAP trend, by removing the IAP from, right, by subtracting the detrended series from the IAP. So this is a series which is there in the data set. So let me run it, and if I plot it, I will have another plot of the trend. So this series is a part of the data set, right? All the trend I saved in the data set. Now I in the file I have the data set in the form of the trend. Okay, my next objective is to analyze the seasonality. So here now I'm showing you how to capture the seasonality. Uh, Seasonal analysis. Seasonal analysis. Okay. Now in seasonal analysis, the you know that in seasonal analysis we have to use the dummy variables which I earlier showed into the data set. So once again I am showing you the data set, let's say names of the file IIP, and if you see the variables you can see in the console, we are having the 12 series, and this is DT means the detrended series, T means the trend. Okay. Now you may be thinking that how I'm using the dummy variables. So to apply the dummy variables, I am just showing you the concept of dummy variables, how it is used in seasonality in time series. Because yesterday I also indicates the use of dummy variables in the models. I start from a very basic thing, how we can use the dummy variables. I hope you will understand the concept of dummy variables after this. Let's say I am having the volatility as a dependent variable, and I'm running a regression model like alpha plus beta into the dummy of Monday plus beta 2 dummy of Tuesday plus beta 3 dummy of Wednesday plus beta 4 dummy of Thursday plus beta 5 dummy of Friday. Now you may be thinking that why I am using this. So there is a concept called seasonality in the time series, and if I ask you that which day is the more volatile day in time series, the research already proved that the most volatile day in the financial markets is the Monday, and after that the next volatile day is Friday. And why Monday is the most volatile day? Because after Friday, whatever news comes in the market, the news comes after the evening of Friday, then news comes after the Saturday, the news comes on the Sunday. Their combined effect will be seen on Monday. So the Monday is found to be most volatile day, and uh, these kind of analysis we can use in dummy regression model. And second volatile day is found to be the Friday. So this regression model is used to capture the seasonality in the series, in the behavior of the market. But the problem is that this this regression model can be run only in two ways. Like either I drop the alpha, or I drop any one dummy. Drop any one dummy. So in econometrics, we are having only two options of running the dummy regression model. and listen carefully that what happens if I drop the alpha and if I drop the dummy. If I drop the alpha, then then beta 1, beta 2, beta 3, beta 4, beta 5 will give me the average volatility on the different days, right? So average volatility on different days. But if I drop any one dummy, then the dummy which I dropped, the volatility of that day is captured by the alpha, and all other beta will represent the difference in the volatility on the different days. So this is the concept of dummy regression model, and in this file, I am using the same concept, but I'm using the concept for the different months. So what I'm going to do, I'm just showing you. So let me explain the concept first, and then I will move. And basically, I am running the equation called IIP equal to, I have the basic equation that beta 1 dummy of January plus beta 2 January, dummy of February, and up to beta 12 dummy of December, and plus error term. So there are two ways of running this model. One is the dropping of the alpha, and the second is the dropping the dummy, dropping one dummy. Now, which method should use? Actually, we cannot say that we can use only method number one, or we can use the method number two. Ideally, we should use the both the methods. So first of all, we use this method, and then we will find out that in which month the average is the highest and in which month the average is the lowest. So after identifying that which month is having the highest IAP and which month is having the lowest IAP, we can select that month and can drop it, right? So I will use both the equations to decide that which dummy variable I should drop and can make the equation. Now I'm running it. Okay, the first equation, you can see that I am putting the 0. 0 means alpha is equal to 0 in this case, and I'm taking all the dummies. Let's say, yeah. So here you can see that I have the data up to the January to December. Now I have to find out the month where the IIP is the highest and the IIP is the lowest. So IIP is found to be the highest in the month of December, and it is found to be the lowest in the month of let's say -6 August. According to this data set, the IIP is found to be highest. This is just after removing the trend. The highest IIP is in the December, and the lowest IIP is in the month of August. So let me select which. No, no, May. In May, the IIP is found to be the lowest, -8. It is the lowest. So let me show you the highest and the lowest values. This is the lowest value of IIP I have seen, and the highest value is found in case of December. So I have two choices to drop the month. I can drop the May, or I can drop the December. So I am going to drop the May because it is the lowest, and I will get all the positive values after dropping this. And in second equation, yeah, I am going to drop the May. So you can see I dropped the May, January, February, March, April, May dropped, June, July, August, September, October, November, and December. So I am putting the December here. So DDEC. So this is a December dummy, and let's run it. And after that, the you can see the values. Okay, now I should run it again because you have to see the whole answer. Uh, if you see the answer or the result of the regression model, the May we dropped, and that value is taken by the intercept, because intercept will always capture the average value of the dummy which you actually dropped. and we are having all the values. These are positive values. These are the differential dummies, right? So the dummy variables are very common in time series analysis, and sometimes we use month dummies, day dummies, and event dummies, right? So dummy variable, you should be very efficient and comfortable in applying the dummy variables in the regression time series analysis. Okay, now what happens after running this model? What is the purpose? The purpose is that if I save the fitted values of this regression model, they are the seasonal effects. So I'm showing you that now I'm going to save the fitted values of this model. Fitted means predicted values, and let me save it. So I saved the values, and you may want to see it. So now I save the residuals also. Okay, let me plot this first. Plot, and I want to plot this fitted values of the regression model. The name of the regression model is REGF. REGF. Okay. So you may want to see the how the fitted values looks like. All right. Let me. Yeah. This is the seasonal behavior, but actually this seasonal behavior is coming like this. We have to take in the data set so that it is shown as a time series, a particular time series, because in this case, the software is not converting it as a time series. It is a result of the analysis. Okay, but it is the seasonality actually which we captured. Now I am, you can see that now I'm going to saving the D trend and de-seasonalized series DDS. Now I'm also going to subtract this fitted values from the original series DT, and if DT minus seasonal, it is called DTS, means de-trended and de-seasonalized series. So this is the residual of the series, and I'm showing you how the series looks like. Okay. Let me see how this series looks like. Yeah. Now the this series is basically this series which is coming after removing the seasonality and coming after removing the trend. So I should write this series as the. So basically, what I did, I just explain again. This is a IIP series. Now, first of all, I remove the trend. After removing the trend, the series becomes DT, D-trended series. Now from the DT, I subtract the seasonality, seasonal behavior. This series is called DTS. So DTS means D-trended, de-seasonalized, and de-seasonalized. So the result you can see here. So after the removal of the series trend and the seasonality, we are having the series in this form, and this series is the series which is found to be stationary, and this series is we can use for the analysis purpose. So this is the mathematical or the process of converting a series into trend series, seasonal series, and any other series. So seasonality, I am showing you how we can plot seasonality. Now you can see seasonality in a time series manner, and this is the seasonality, and we are having two things here. So you can see in a particular month the IIP is found to be the highest, and in a particular month the IIP is found to be the lowest. So now we know that this is a May month the IIP is found to be the lowest, and in the month of December the IIP is found to be the highest, right? So this is the result of the seasonal analysis, and I hope it seems interesting. And this is the first basic lecture on time series. And as we move in advance, we will see so many other analysis um, in time series. Okay, let me move again. Okay, now finally I have seen, I've shown you all the methods of de-trending and de-seasonalize each and everything. So I hope you are happy here. Okay, now I am moving to the further analysis of the time series. So up to this level, I just show you how to convert a normal series into a time series, and how to decompose the time series and time series data set. And this is a repetition, so I should remove it. Yeah. We are having the commands in the software that which will directly do this, and I just remind you one thing again. I can have decompose function, automatic decompose function in R, and we are having directly decompose all these things manually by just one command. So, but as a time series econometrician, I know that we should know the background of this command, and so that we can use it whenever required. Okay, now I'm telling you the basic properties of the time series, and I will show you how to do that. Let me explain the concept of the time series. In basically the time series, the problem is that whenever you apply the regression model between two time series, the R square is found to be very high. So this is a problem. This is actually a problem, and let me explain the concept first. Then I will show you the problem. In time series, suppose I am running the regression model. The regression model is like this: that yt equal to alpha plus beta 1 into xt plus erratum, or you can add some more variables. In this case, yt means y is a time series, xt is also a time series. So in this case, if I run it, I have to check two things. Number one, what is the value of R square? And second thing which I should see is what is the value of Durbin-Watson? Because in time series analysis, this Durbin-Watson is playing a very important role. And when the R square is more than Durbin-Watson, and when or Durbin-Watson is less than 1, then this regression model, which you can see above, is known as nonsense model. And if you make a nonsense model, you know that what happens to you, right? Because most of the time I have found that anybody who is not clear about the time series data set, they normally go for a nonsense time series, and um, their paper always rejected if you do this kind of basic mistake. So what is this concept? Actually, we need to understand that. Okay, let me explain this concept further. So I am saying that there is a concept of nonsense time series model. Nonsense time series models. So nonsense time series models comes when the Durbin-Watson is less than 1 and R square is high. R square is very high. Okay. So to understand that, I divide the time series into two categories. So I divide the time series in two categories. One is called random walk, and second series is known as the stationary series. Stationary series. So we have to understand that what is random walk and what is stationary series, right? What is random walk and what is stationary series? Because if you do not understand these concept, no analysis in time series is possible. So let me explain you this concept. Okay, suppose I run the regression model that yt is equal to alpha plus beta into yt minus 1 plus error term, right? In this case, let's assume that alpha is equal to 0. So I put alpha is equal to 0, and let me remove this alpha, and the equation becomes this. Okay. Now in this case, you can see that yt, which is the value of y on any day, is either predicted by yt minus 1 or is predicted by et on that day, error on that day. Let me explain you another way. Okay, let me write yt is equal to alpha plus beta in I'm sorry, ये alpha दोबारा आ गया. Yt minus 1 plus et. So this is the series. Now I am saying that this yt is either influenced by its previous value or the error term. Right. Now, suppose today your age is 28 years, and I'm asking that what is the age after 1 year? So you say that it is 28 plus 1 is equal to 29. So this kind of series is called deterministic series. Deterministic series. But do you think this kind of forecasting we can use in stock market or exchange rate or forex market, commodity market, right? Deterministic series. So most of the financial time series are not deterministic, they are stochastic, and because of the stochastic, this relationship is not possible. So I remove this model. Because in finance you cannot say that today the price of lens is 1,000 rupees and tomorrow it is 1010. The stock price will not move in this way. The stock price will move randomly. Sometimes it comes down, sometimes it move down. So on what basis it comes down and move up? I am saying that the stock price or the commodity price or the exchange rate or any other time series data set depends not upon its previous value, rather it depends upon the error term, et. So if positive error come, it means the positive movement is there in the y. If negative error comes, it means negative movement comes in the y. So the series is not affected by the previous value, rather it affected by the error term. This concept is explained by the professor who gave this concept. I'm telling you the concept in similar way. Suppose suppose a drunken person, a heavily drunken person, and we are predicting that in the which direction he will move. So he can move in the different directions. Like you can see, he can move in the different directions. So these are the different directions in which he can move. Now which variable is responsible of the next movement, right? So how can we say that the person can move in this direction only, or this direction only, or this direction only? So how can we say that in which direction the person will move? Actually, it depends upon the random thought which comes into his mind, that maybe he is thinking towards moving his friend house, so he can move in this way. Suppose he want to move to the market, he can it is a random thought that let's move to the market, let's move to the friend, let's move to the house, let's move to the shop. So there are different random thoughts which come into his mind, and according to that he will move. So these random thought which comes into his mind is a proxy of the random news which comes into the market, because we don't know tomorrow which kind of news will come, right? Tomorrow negative news may come, tomorrow positive news will come. So similarly, if the stock prices today is this, so stock price can move up by different directions. So these are the possible directions of the movement of the stock tomorrow, and the stock if move down, this is the possible movement of the stocks. So when the stock movement depends upon the error term, this concept is called random walk. So in most of the time series, we are having the concept of random walk, and in the random walk, three properties are there. So I am writing the properties of the random walk. And so these three properties are: number one, the mean is not a constant, right? So the mean changes with time. Second, the variance is also not constant. And third, the covariance between any lag I t minus I. So this is the covariance between any two lags is not constant. These three properties are there in a random walk, and opposite to it, I can write the properties of a stationary series. So there are three property of the stationary series. Number one, the mean is constant. The number two, variance is constant. And number three, the mean constant, variance constant, and the covariance between I and t minus I is also constant, right? So if I show you that how this series moves look like, this is a basically is a non-stationary time series. This series which I make here is a non-stationary time series. And if you understand what is stationary series, identifying a non-stationary time series is very easy. The stationary series looks like this. The stationary series is look like this. This is a stationary series. So you can see that in this series, the mean is constant with time. So it is called time reverting, right? Uh, so it is coming back to its mean. The series always comes back to its mean. So it is mean is time reverting, or time it is constant. Second, the variance is also constant. You can see that you can pick any of the sample, and you found that the variance of the time series is also constant. So variance is also constant. And third thing, which we cannot express by this graph, but the covariance between any two lag, the covariance between I and t minus I is also constant. So if this property is there, then we can call this series as a stationary time series. Okay. Now, in case of stationary time series, if you apply any regression model, or it will work. Otherwise, all other analysis will not work in. So I'm writing which kind of analysis you can do in random walk, and which kind of model you can do in a stationary series. So because for a learner of time series analysis, you must know what kind of analysis we can do on the random walk, and which analysis can be possible only in the stationary series. Like in random walk, you can do the trend analysis, you can do the growth analysis, and you can do the co-integration analysis. You can do the quantile regression and all. In stationary series, the ARIMA is applicable only on a stationary series. Garch model is only applicable on the stationary series. VAR model and Granger causality is possible only on the stationary series. The time series regression is only possible on the stationary series, right? Here you apply the Kalman filter, and you can apply the wavelet time series, wavelet decomposition, and so there are different models you can see here, and you should know which series is required and when. If you are going to apply a regression model, or you are going to apply vector order regression model, or you are going to apply Garch model, ARIMA model, then you need the stationary should be stationary. Even if you are going to apply logit model, probit model, it is expected that all these series should be stationary. So I hope now how you know that how the stationarity concept is very important in time series. Now the question is that how to check the stationarity of a series. How to check whether the series is stationary or not. So my next topic is that decide how to decide whether the time series is stationary or not. Whether the time series is stationary or not. Now, what is the answer? Answer is the unit root test. Answer is the unit root test. So you have to apply the unit root test to decide whether the series is stationary series or not. So now I'm going to explain the concept of unit root test, so that you must know how to apply unit root test, how to interpret unit root test, and what is this unit root test. So let me explain the concept of unit root test first. As I said that random walk can be explained by, let me write, random walk is explained by the series called yt equal to beta into yt minus 1 plus et. And the assumption is that if beta is equal to 1, it means the series is random walk. It means the series is random walk, right? Now, we cannot apply this equation. So what we do, we subtract the yt minus 1 from the both the sides, yt minus 1, and beta yt minus 1 minus yt minus 1. So you can see that I'm subtracting this part from both the equations, and et. Now yt minus 1 means today price minus yesterday price. It is known as the change in price. So I can call it delta yt. Similarly, I can take yt common here. So it is beta minus 1 into yt minus 1 plus beta et. And this equation I'm rewriting as sigma yt is equal to delta yt minus 1 plus et. So this equation is the equation of the Dickey-Fuller test. So this equation is known as Dickey-Fuller test, DF test. Dickey-Fuller test. Now the assumption of Dickey-Fuller test is that delta is equal to 0. So here the null hypothesis is that delta equal to 0, because if delta equal to 0, then beta minus 1, which is equal to delta, then beta minus 1 equal to 0. So if delta equal to 0, then beta minus 1 equal to 0, it means beta is equal to 1. So it means beta is equal to 1, and your null hypothesis will be accepted, cannot be rejected. So we can identify the unit root, whether the series is a random walk or whether the series is not a random walk. This is the concept of the unit root test. But the problem is that this equation is later on highly criticized, and many people say that this equation is not a good equation because this equation itself is suffering from a Darwin-Watson problem. So you should modify this equation. So after that, the Dickey-Fuller modified this equation, and the modified equation is known as augmented Dickey-Fuller test. So now I'm showing you what is the augmented Dickey-Fuller test. Basically, he modified this equation like delta yt is equal to alpha plus beta into time plus beta 1, beta 2 into delta. No, sorry, it is not delta. It is delta into yt minus 1 plus summation of I equal to 1 to n, and it is a gamma, and it is, we can write here yt minus I, and t minus here I is equal to 2 plus et. So this equation is known as ADF test, augmented Dickey-Fuller test. Now in augmented Dickey-Fuller test, what we are doing actually, we are capturing the intercept, we are capturing the trend. This is for trend, and this is called drift. Drift means short-term momentum in the movement of the time series. So we are capturing the drift, we are capturing the trend, and the null hypothesis of this test is that delta equal to 0, or in simple words, we can say the series is a random walk. So basically, this hypothesis you should know that what is the null hypothesis of ADF test. The series is non-stationary, or a series is non-stationary, or a random walk. So this is the null hypothesis of the ADF test. And if probability value is less than 0.05, You should be happy because your series will be stationary. Okay, now I am going to show you how to run the ADF test in R, uh, so that we can understand what the is the meaning. Okay, so these are the packages I am going to use, and so let me run it. Now I am going to open a file that the name of the file is economic variable. So this is my data set, and in this data set you can see that I am using the data of many economic variables here, and this is PVIX, this is IVIX, this is a volatility index, and FII investment, DI investment, trading volume, PE ratio, 10-year government security interest rate, USD interest rate, and exchange rate and interest rate, right? Now, I'm showing you the regression model, a simple regression model. Here I am taking the USD INR, means exchange rate is a dependent variable, and I believe that this variable, it depends upon the interest rate and the P ratio and the FI data. So what happens if I run this regression model? Let's see. Let's run the regression model. In this regression model, you can see that the R square value is 22%, and all the variables are significant. So now frankly speaking, this result is enough result to report in a paper and to write a paper. But before moving that, I have to check whether this regression model, it is a time series regression model, and I want to know that whether this time series regression model is suffering from the Derwin-Watson problem or not. So I am going to apply the VIF first, and here you can see that all the VIF is less than 3. So multi-collinearity is not a problem in time series. In most of the cases, we don't have multi-collinearity problem in the time series. Now I am going to apply the Derwin-Watson test. Okay, Derwin-Watson test. The result is the Derwin-Watson is 0.028. So this is a common mistake done by almost every researcher when he is not aware about the random walk concept. You apply the regression model and prove that all variables are significant. You can see that in this equation, all the independent variables are significant. It means the model is very good, but actually this model is not good. This model is actually a nonsense model, because Derwin-Watson value is less than 1. And if you show this model in a research paper, the person will reject immediately. Okay, now Derwin-Watson value is 0.028. It is a not good. Because this problem comes only when you are not aware about the Derwin-Watson concept. So I have to check whether my series is a stationary series or not. So now I am going to apply the ADF test, which I explained just now, and I am applying for USD first of all, and let me check it. So you can see that I am applying the Decomposition test. Lag order 0, p value is 0.53. So p value is 0.53. So as I said that the assumption null hypothesis of the Decomposition test is that the series is non-stationary or the series is random walk, and here probability value is found to be 0.5853, which is greater than 5% level of significance. Because the p value is higher than the 5% level of significance, so it means the series is actually non-stationary. So we are getting the nonsense regression model. And let me check other series also. Okay, let me check all the series which I put in the regression model, and let me show you the results. So here p value in this case is less than 0.05. So p ratio is a stationary series. This is a random walk. This is a stationary series, and this is also a stationary series. So in this case, two variables are found to be significant, and two variables are random walk, and two variables are the stationary series. So because our dependent variable, you can see that here this value and this value is more than 0.05. So this kind of analysis we should do in the advance, so that we can identify that which variable are non-stationary and which variables are stationary. Okay, now the problem is that similarly I am showing you another regression which I put here in this equation. Okay, check. Now in this equation you can see that yeah, this equation is having the Durbin version of 2. So this equation is not suffering from the regression model, the problem of Durbin-Watson test. And uh, now you may be thinking that how to achieve this kind of regression model where Durbin-Watson is near to 2. You know that when the Durbin-Watson is near to 2, it means this model is a genuine model, and this model is not suffering from the autocorrelation problem. Now I am telling you the way which we can apply this kind of regression model. In previous regression model, two variables are not stationary. One is the exchange rate and one is the this GSEC. And here I remove uh, the USD INR by exchange rate, and I remove X10 GSEC by INT interest rate. And the transformation which I applied here, I'm just explaining the transformation to you. And basically, whenever I want to convert a stationary non-stationary series into a stationary series, I am doing a log difference transformation. This is called log this difference transformation, and this log difference transformation is simply y is equal to log yt upon yt minus 1. So whenever we found that the series is non-stationary, in more than 90% of the cases we use this transformation. So after the transformation, you can see that we will get the stationary series. And if you want to see the transformation process, I can try here also. Okay, so let me show you the transformation which kind of transformation we applied. Let me try it here. X rate is my transformed variable, EXR8E, and I take the difference, DIFF difference of the log of the variable called USD INR. Okay. Now this is the transformation, and I want to see the difference between the series. So I should write USD. This is the original series, and this is the transformed series X rate. And I can show you both the series. Yeah. So both the series are here, and okay, so by looking at these values, you are not able to find out what is the difference. So let's plot the USD first, and yeah, this is the plot of USD. It seems to be random walk, and if I plot the X rate, and this plot will come to be a stationary series. Let's see. Now this is a stationary series. So I hope you understand that how we transform a variable into a stationary variable. And after the transformation, if you do this, then you can apply the regression model. And if I apply the ADF test of the transformed variable, and you can see that this will be the stationary variable. So now let me show you the X rate. So I am showing you the ADF test on the X rate transform series, and you can see that it will be definitely stationary. Now you can see that now after the transformation, the series becomes stationary, and we are happy that we got the stationary series, and we can use these transformed series into the regression model. So this is the rule of ADF test. After this ADF test, we are also making some of the tests like auto regression. Let me show you the table. Okay, so in this case, you can see one graph. So this is called PACF graph, and similarly we can plot ACF graph. So this PACF graph and ACF graph are also useful in identifying whether the series is stationary or not. Mostly, if you see the PACF graph.
क्या करोगे विजय पांडे बन रहे हो क्या विजय पांडे भी डायरी ले
Hello. Okay, some noise in between. So if you plot a PACF graph, and the first spike of PACF is if it is equal to 1, then it is called non-stationary, and if it is not equal to 1, that is called stationary. Like for example, we know that this USD INR is a non-stationary series, and if I make a PACF plot, and you can see that let me show you the PACF plot of USD INR. Okay. Now, what is the difference you can find out? You can see that the first spike of the PACF is found to be 1. This is one of the other tests of testing whether the series is a random walk or not. So here you can see that the PACF stands for partial auto correlation function, and partial auto correlation function is a very useful function which we can use in ARIMA forecasting, Verimax forecasting, or any other forecasting. And PACF is found to be 1 at 1 lakh. And if I plot PACF of the transformed series, that is called X rate. And here, because we know that exchange rate is a stationary variable, so we will get the PAC. Okay, the spelling is mistake. PACF. Now you can see that PACF, in this PACF, the first spike is not equal to 1. So this is a stationary series. So we are having this data also to find out whether the series is a stationary series or not. Similarly, we can plot ACF and PACF of different variables. And if I put the PACF of the regression model, we are having this kind of values, ACF and PACF. So autocorrelation function and PACF correlation function are also very useful in time series. And we are having different kind of ACF and PACF functions. Yeah. And in this case, yeah, so my topic is complete, and I have finished this topic. There is one more case study of this unit 2 test, and here I'm just showing you the results, and I hope you can understand what I'm going to do here. So it is basically the case study of the unit 2 test on the Nifty series, case of unit root on Nifty index series. First of all, I am showing you the data set. So this is my data set. I am having this data set. It is a daily data of the Nifty or monthly data of the Nifty. It is a monthly data of the Nifty. And if I plot the Nifty, so you can see the plot here comes here. The behavior of Nifty in the past many days. And if we plot ACF and PACF of Nifty, let me check PACF first. You can see that in PACF, the first lag is found to be 1, almost 1. So it is originally non-stationary, and the ACF is coming like this. So this is called geometrically drying function of autocorrelation. So when we are having the geometrically drying function and PACF equal to 1, then it is called non-stationary time series. and I am also showing you that how to check it with the help of ADF test. Now, if I run this test, the p-value must be more than 0.05. Yeah, you can see that the p-value is more than 0.05. It is almost 0.30. So here we can conclude that this series is a non-stationary series. Now I am converting this series into the stationary series. So this is a log difference function. After converting the log difference function, yeah, then I want to plot this return of Nifty. I call this name as R Nifty, return of Nifty. And how this looks like, yeah, this looks like this, and it is showing to a mean reverting process. Mean reverting process seems that it is a stationary series, but I want to confirm it. So I will apply this test once again on, yeah, ADF test. Yeah, the command is already there. So if I apply ADF test, the answer will come in the console, and now you can see that the p-value is found to be 0.01. So let me run it once again. So here you can see the p01. So after the log transformation, after the log difference transformation, we can convert a series into a stationary series, and after that we can use this series into the regression model. And if you plot ACF and PACF, you will not get the geometrically dying ACF and first spike equal to 1 in PACF. So let me show you the ACF first, and I'm sure that it is not a geometrically dying function, and the plot will come in the plots. Let me show you the plot first. Yeah, so this is not a geometrically dying function of autocorrelation, so it is a stationary series. And similarly, if I plot PACF, then PACF is coming like this. It is not a, in this slide you can see the first value is not equal to 1, so it is a stationary series. So this is the two things which I will show you. Now I put my session and you are most welcome to ask any query. So thank you very much. Thank you for your patience listening. I know that the topic is complicated, but I try to explain at my best. So thank you very much. If any queries there, please ask.
Sir, there was one query, I think. Let me.
So before that, I just want to say one thing. My name is Dr. Ajay Kumar CHauhan. I have a YouTube channel in the name of Research Shiksha. You can see some of the video lectures there also. Thank you.
Sir, there was one question about how to basically convert non-stationary time series data to stationary model.
There are many methods of converting the non-stationary series into a stationary series. Number one, remove the trend. Number two, remove the seasonality. Number three, take the log difference transformation. Number four, take the ratio. Number five, take the simple differencing. So these are the different methods of converting a non-stationary series into a stationary series. It depends upon the series also. So first of all, we should know the nature of the series, and then we try to transform it. Before that, I just want to say one thing. My name is Dr. Ajay Kumar CHauhan. I have a
So
YouTube
thank
channel
you so much, sir. Your lecture has been immensely informative and explanatory. We thank you for expecting our invitation so promptly and sparing time to deliver the lecture. Thank you so much, sir, and have a great day ahead. Thank you so much.
Thank you. Thank you.
Thank you so much, sir.
Thanks, Sachin.
Thank you, sir.
Okay, thank you. Thank you. I'm leaving.